Okay, well, I make it 7 o'clock, so we'll get started. Hopefully everyone can hear me okay. So welcome to Sherwood Observatory Live. It's a bit like stargazing live, except without Dara O'Brien and Brian Cox. So hopefully we'll do instead. I'll just start to run the slideshow, and then I will tell you what we've got in store tonight. So who we've got online tonight is myself, Steve, and Brendan. So I'll be talking about the James Webb Space Telescope. I'll start off by giving a presentation on what it's about and what it's going to do, and then include a demonstration of the infrared camera that will be carried on board the spacecraft. I'll then hand over to Brendan, who will be talking about the Orion Nebula. We were hoping to do some live views of the Orion Nebula through the telescope today via a webcam, but it's cloudy, so I think Brendan's got one that he prepared earlier, so he'll be running that instead in due course. We've also got Chris and Rob, who will be monitoring the chat, so if you have any burning questions that you don't want to wait until the end, just type them in and they'll do their best to either answer them or remember to ask them towards the end of the presentations when we'll have time for questions. So I just wanted to start by just saying a couple of words about our observatory. So this picture on the left is our observatory pretty much as it is today. The dome's a different colour. So that houses a 61 centimetre Newtonian reflecting telescope that was built by the members out of essentially recycled materials. The observatory has been going for, well, the society that started the observatory celebrated its 50th anniversary last year. And we continue to develop the observatory. When in normal times, you can come and visit the observatory either by a pre-arranged group visit. We cover adult groups, children's groups, school groups, that sort of thing. Or you can just come along on one of our open evenings. And we used to run pay on the door, but I think given where we're going with lifting lockdown restrictions, we're probably running ticketed events, but essentially you can just come as individuals or a family and come along to it. We also, in the summer months, go and take some of our kit to festivals and demonstrate what we do at festivals and things like that. It's a popular place, so we've got plans to expand, and next door to the observatory we own a redundant underground Victorian reservoir, and you can see that in the picture on the right there. So that's what it looks like today. It was built in the 1880s as temporary storage for water to supply the local area. What we want to do is turn that into a visitor centre, a science discovery centre, and a planetarium. And we'll be doing a lot of work on that over the last year and before. And we hope that it will look like that when it's finished. So that's right next door to the observatory. The image that you can see there is based on some work that some architect students did from Nottingham University, and then they were rendered into these almost photorealistic images by a company called Block Digital, and both of those organisations gave their work for free. So thank you to them. We do need to raise money to make this happen, to provide some of the matched funding for the next stage. So if you like what you see this evening and you'd like to make a donation, just go to the site that's given on this page here, or drop me an email. Or if you go to our website, you'll find all those links on our website there. So if you just Google Sherwood Observatory, you'll find us. So without further ado, I'd like to go into the first part of the presentation, which is to talk about the James Webb Space Telescope. So why are we doing this? Well, the Webb telescope is being partially built in the UK. Some of the instrumentation that's going to be flying on it is built by UK scientists. And we've been fortunate enough to be selected to work with some of that team to help them in their public outreach. So some of the materials I'll be presenting tonight, and it'll be coming from that. And I'll be doing a demonstration of a camera that works at the same wavelengths as the camera that will be carried on the James Webb telescope. So I'm just going to go through, first of all, the description of the telescope, and then briefly touch on some of the science that we'll be doing once it's launched. So everyone's, I guess, familiar with the Hubble Space Telescope. This is a picture of Hubble. It's you can see there just sitting above the Earth's atmosphere, and that's produced some absolutely fantastic images over the years that it became world famous. The reason why it's sitting above the atmosphere is because you get a clearer view from up there. You're out of the air, so there's no turbulence, there's no dust, no pollution, all that sort of stuff that affects your view. So it can produce images like this. This is the pillars of creation in the Eagle Nebula, and that's something like somewhere between 6,500 and 7,000 light years away. So we're seeing this as it was 6,500 to 7,000 years ago, and Hubble's produced many, many more images of this sort of quality that are great to look at, but also allow science to be done when you study those images properly. So how does Hubble compare with the James Webb Telescope? Well, there are other telescopes in space as well, but you can see Hubble there on the left. It's got a 2.4 meter diameter mirror. The size of a mirror in the telescope is important because the bigger the mirror, the more light you can collect, so the fainter the object that you can see. So if you compare the Webb telescope to that, you'll see it's got a much bigger mirror. So that mirror is something like 7 times the area, 7.5 times the area of the mirror on Hubble. So it will be able to gather 7.5 times as much light. You can see there, unlike Hubble, it's not a single mirror. It's actually made up of 18 hexagonal sections all joined together, and I'll come on to that in a little bit. And you'll see just from the design of the spacecraft itself, it's very different. All these other space telescopes are sort of tubular devices that fit neatly in rockets. You'd be struggling to put this in any sort of spacecraft in its deployed form like that. So I'll touch on to that as we go through. So the other unique thing about, well, not unique thing, another thing about the James Webb Telescope is that it doesn't use the light that we can see. It uses a different wavelength of light. So this image here just shows a spectrum of light. You'll see exactly the same thing if you see a rainbow in the sky. And all that is the visible light that our eyes are sensitive to, split into a range of different wavelengths and different colors, going from purple all the way through to red. And you can see on the animation there that those different colors come from the different wavelengths of the light, purple being a short wavelength and red being a long wavelength. And there's no reason to expect why those wavelengths should stop at the edges of our vision, just what our vision's used to. And in fact, they don't do that. They extend in each direction downwards to the screen, shorter and shorter wavelengths, and you get into X-rays and gamma waves. Going up the screen, first of all, you get into infrared, and then if you keep going far enough, you get into radio waves. They're all part of the same spectrum. And the James Webb Telescope operates in the infrared band, so it doesn't operate in the bands where we can see. It operates at longer wavelengths. So this is just an example of the sort of thing you'll see in infrared. So we have a normal visual sort of wavelengths, a picture of a cat on the left here, and then on the right we've got an infrared image of a cat. Now the reason why we can't see it, of course, is because the camera has converted those wavelengths that we can't see into a grayscale black and white image that we can see. And the areas of that image that are brighter correspond to the areas that are giving out more infrared radiation. Warm objects give out more infrared radiation than cold objects. So you can see the bits of the cat that aren't so insulated with fur, like its ears and the front of its face and its paws, are glowing brighter than the areas where it's covered in quite thick fur, and that's acting as insulation. So it's just looking at a different wavelength. The other thing that you see in infrared pictures, you often see pictures, so that one on the left is just the repeat of the black and white picture on the previous frame. The one on the right is exactly the same image, but in false color. So there's no more information in that image on the right than the one on the left. It's just some people prefer looking at color-coded images than black and white. And when we get onto the demonstration of the camera in a little while, I'll be using a color scheme that looks a bit like that, but they're completely false, those colors. They're just to help us visualize what's going on. So the camera that took those images of the cat works at the same wavelength as one of the optical instruments on the James Webb spacecraft. And this is one of those instruments. it's called MIRI, which is the mid-infrared instrument, because that's the wavelength it operates in. And it's showing here, covered in its foil protection, mounted on the frame that it'll be using when it goes into the James Webb Telescope. Now, this instrument was designed and built in the UK, and the project lead is Gillian Wright, just shown in the image down there. And one of the benefits we've had as a society is access to some of the people, so we can ask them questions on how that was built, and some of that's feeding into this presentation. So, but the important point to get across here is that the UK has been very heavily involved in the James Webb Telescope design, and particularly the science packages. It's something the UK excels at, actually, is satellite technology and the science around space technology. The other thing about infrared, as I said earlier on, infrared it comes from bodies that are warm. So what you need to do is cool your camera down, otherwise all you'll do is pick up the radiation signature from the camera itself. So there's essentially a space fridge fastened to the MIRI instrument pack, and the job of the space fridge is to get the temperature of the camera and the associated systems down to -266 degrees centigrade, which is nearly as cold as it's possible to get. The absolute temperature you can get down to is -273, so it's pretty close to the actual coldest temperature possible. And as I say, the reason for that is because if you didn't do that, you'd just be picking up radiation from the instrument. So it'd be a bit like building our optical telescope, and instead of using scaffolding poles painted black to build the frame, it'd be like building the frame of our optical telescope out of fluorescent light tubes. And that would clearly cause a lot of light pollution, and it'd ruin the view. So that's the equivalent of the optical in the infrared. You've got to cool it right down. This is just another image of the instrument frame on the telescope. So this is the kind of core frame, and everything gets bolted into that. And this is the mirror cell setup going in. So here you can see they're assembling the various hexagonal mirrors into place, ready to go onto the spacecraft. Now, if you've got one solid mirror, you can grind it so that you get an optically perfect surface to collect the light. If you're joining 18 mirrors together, you can grind each mirror to be perfect, but then you've got to make the join between the mirrors perfect. And that was quite a task. And the accuracy to which they've had to join these 18 mirrors together is to within 1/10,000th of the thickness of a human hair. Now, in practice, you can't just screw something down to that accuracy. So what each mirror cell has is little actuators that they can switch on and move around to get it just perfect. But as I say, to 1/10,000th of the thickness of the human hair, that's what they have to get it down to. The other reason why you need multiple mirrors, apart from the size of the thing to launch, is that if you try to make one big mirror this size, you'd have to make it very thick, and then that would be too heavy to launch. Each of these mirrors weighs roughly 20 kilograms. So altogether, this whole bit, including the frame, is probably about 720 kilograms, so well under a ton in size. So this is the assembled set of mirrors in place. The sort of pyramid thing sticking out of the middle is the light path into the cameras and the other sensors. So light reflects off this. This isn't deployed at the moment, but this strut here, these struts here, hold the secondary mirror. The light comes in, bounces off the main mirrors, hits the secondary mirrors, and then gets reflected down this tube in the middle, which is why there's not a mirror right in the middle. And then all the optical instruments are sitting behind that. So that's very big. Remember, that's 6.5 meters across. And this is the other main component that you notice. And this is a heat shield. So this has got 5 layers of reflective coating, and the purpose of that coating is to reflect heat away from the telescope, again, to keep it cold. Now, if you look at a piece of tin foil, it's about 0.2 of a millimeter thick. These things are about, if you stacked all of these thicknesses together, it still wouldn't be the thickness of a piece of tin foil. So this is quite a fragile structure, so they have to be very careful putting it together and assembling it. So this just shows the purpose of that big area of essentially tin foil. It's to protect the telescope from heat and from light, which would spoil the view. So it acts as a shield between glow coming from the Earth and glow coming from the sun. So that means on that side of the telescope, it's at about 109, 110 degrees C in space with the sunlight. On the dark side of the telescope, it gets down to about minus 220 degrees centigrade, and that's the sort of temperatures you need to make the instruments work. But there's a bit of an issue there, isn't it? When you look at that telescope and you think that that mirror is 6.5 meters across, and it's about the size of a tennis court if you took all those 5 areas of that reflective material and spread them out, you've got to get that into space somehow, and there's no spacecraft big enough to carry that in that format. And even if you did try and launch it like that, it would probably be too fragile and you'd likely snap something or break something. So the mission scientists had to think of a way around that. And so the next few slides will show you what they came up with. So again, this is just a picture of the telescope under construction, and you can see this time that that big silver flat area has been concertinaed together. So it's almost like origami, and that has to fold up to go into the spacecraft to be launched. And again, the mirrors wouldn't fit in the spacecraft without folding up. So the 3 outer cells on each side are hinged, and they fold back, as you can see in that picture there. And remember, when they fold back out again and get adjusted in position, they've got to be in position to within a 10,000th of the thickness of a human hair. So that's a real engineering feat, getting that to work like that. If you talk to space scientists, they say the last thing you should be doing in space is having moving parts, because if you're on the Earth, of course, if you've got something like a car with moving parts, you put oil or grease on it and that keeps everything lubricated. In the cold of space, if you try using oil or grease, it'll just freeze solid and everything would stick. So one of the big challenges has been to design this in a way that it actually works in the cold of space and it all unfolds once it gets to where it's going. So these are just a couple of images of showing it folded up. So even when the reflective coating is being folded up in one dimension, it still won't fit into the spacecraft. So then it has to hinge up to either side of the mirror and get folded up. And you can see there that in that format, it can fit inside the nose cone of the rocket. So that's what it's going to look like when it's launched, and then it's got to unfold once it gets into space. And again, just another image here showing the way it's folded up, and the 3 mirror cells there folded to one side, and the same on the other side. You'd see the other 3 mirrors folded to one side as well, sitting on top of an Ariane 5 rocket there in the bottom picture. Now, the other thing about Hubble, it's in Earth orbit, and the Earth glows quite hot in infrared. So if you parked the Hubble Space, the James Webb Telescope there, you get a lot of light pollution from the planet itself. So that's not a good place to park the James Webb Telescope. So as well as the heat shields, it has to go somewhere else. And where it's going to be parked is one of the Lagrange points. Now, what they are stable gravitational points where something you put at a Lagrange point will pretty much stay there. So if you look at the Lagrange points 4 and 5 for Jupiter, for example, you'll see quite a lot of asteroids there because they're in a stable position, and they'll just follow Jupiter around and around the orbit and remaining in those relative positions. So what they're going to do is put Webb at L2, which is, by the way, this isn't to scale, of course. The sun is a lot further away from the Earth than would appear according to the diameter of both that we've got here. But it means, as you can see from the relative positions, that the Webb telescope is going to be parked beyond the orbit of the moon. And the advantage of that, because it's a stable point, is that as the Earth orbits around the sun, Webb will stay in the same place, so it'll always be shielded from the sun by the Earth, as well as its heat shields. But that means it's 4 times further away than the moon is, so 1.5 million kilometers away. If people remember back to when Hubble was launched, there was a fault and they had to send a space shuttle mission to it to repair it. Well, this is 1.5 million kilometers away. No human has ever traveled further than the moon, so this is out of range of our ability to go and fix it if anything goes wrong. So they've got to get it right first time. Everything's got to work first time. So finally, I just want to go through some of the missions and not very much detail. what's going to do? Well, it's a big mirror, so it can look at fainter objects, and fainter objects means that you can see them further away. And in the context of space, further away, because of the speed of light, means you're looking back further in time. So it's going to look back right to almost the beginning of the universe and have a look at what the first stars were that formed, and what the first light in the universe really was. It's also going to look at how galaxies form. How were the early galaxies formed? What did they look like? Well, they probably didn't look like this, but that's one of the missions are going to find out. And they genuinely say the most exciting thing about Hubble is, about Webb, is that they don't know what they're going to find. It is genuinely a mission of discovery. They're going to look at exoplanets. They're planets that orbit around other stars. And one of the things Webb will be able to do is to analyze the atmospheres around those planets. And if you think about planet Earth, the reason why we have 21% oxygen in our atmosphere is because of life. That all comes from plants and microorganisms. So by analyzing the atmosphere of other planets, Webb might be the first mission that we've got that actually finds life orbiting another star. So that's something to look forward to and look out for. It'll also be looking at planets in more detail in our own solar system as well. And the final thing that we'll be doing is looking at the birth of stars and the birth of planets. So this takes us back to the pillars of creation again, just in optical light. One of the things that infrared does, it can look through all those clouds of gas and dust that are busy forming stars. And so the sorts of images that we get using Webb are something like that, and you can see there you're starting to look through all those clouds of gas and dust and see what's going on inside of them. So that's just some of the exciting stuff that Webb is going to be doing. And so watch out for the launch. It's due to launch in October this year. Quite a nervous experience, I would imagine, for some of the mission scientists. The MIRI instrument I've been talking about, there's been people working on that for a couple of decades. And that instrument is now being strapped to the top of a rocket, and they're going to light the blue touch paper and stand back. So you've potentially got 15, 20 years of work going to blow up if that goes wrong. So everyone will really have their fingers crossed on the launch. And I would imagine they're live streaming that. So when you get to October, look out for that happening. Okay, so now what I'm going to do, just very briefly, is just do two demonstrations of a camera that works at the same wavelengths as the camera on the MIRI instrument on Webb, just to show you very briefly the importance of, first of all, why you put these things in space, and secondly, the benefit you get from using infrared wavelengths. So if you just bear with me for a while, I will switch to my other screen. Okay, so now you should see the view of the camera that I'm using. If Chris could just put his thumbs up and confirm, that would be good. Thank you. Okay, so this is the camera, like I say, works at the same wavelengths as the infrared camera on Webb. It also works in optical wavelengths, so we can see what's going on. So we're just using normal visual wavelengths at the moment. And you can see, I can put my hand in front of the camera, and of course you can see that. If I put my hand over here, you can see that as well. Now, what I want to demonstrate here is why we need to put these things in space. And the reason for that is because some wavelengths of infrared can't penetrate all the way through the atmosphere. It's one of the reasons why we have global warming and climate change, is because sunlight comes down to the Earth, warms the surface, it re-radiates in infrared, and molecules in the atmosphere like carbon dioxide absorb that infrared radiation rather than letting it through, and the planet warms up. It's called the greenhouse effect. So this just kind of demonstrates that. I couldn't get enough atmosphere in my office to demonstrate how thick an atmosphere you need. So we have this sheet of perspex here that will do the same thing, sheet of perspex there. So I'll now just switch to infrared wavelengths, and you'll see what I mean. So there we are. So now we're running on infrared. So if I put my hand in front of the camera, you can now see my hand's warm. So it's glowing in infrared because it's warm, giving off energy. If I now slide my hand behind that perspex sheet, you can see that you can't see it anymore. And that's because, like a large thick layer of the atmosphere, it's not letting the infrared light through from my hand, so the camera's not picking it up. So that's just a quick demonstration of one of the reasons why you'd put it in space. The other reason, of course, is because the whole of the Earth's glowing, so that would spoil the view as well. I'll now just go on and quickly show you the second reason. So back to optical again. This time, my prop is a cat litter bag, unused, I hasten to add. So this is a cat litter bag. For the purposes of this demonstration, this cat litter bag is a nebula of gas and dust in interstellar space, which is acting as a star-forming region. So we can't see inside of it at optical wavelengths because of all the gas and dust. But if I now switch to infrared mode and drop the menu, now you can see through the gas and dust, and you can see my hand inside of the cat litter bag. So remember, the cat litter bag is playing the role of the gas and dust, and my hand's playing the role of the stars that are forming inside of that layer of gas and dust. So it's like that second picture of the pillars of creation that I showed. So that's just a very quick demonstration of some of the capabilities of an infrared camera. Okay, so without further ado, I will hand over to Brendan, who's going to take you through talking about the Orion Nebula and the constellation of Orion in general, I think.
Hi, thank you, Steve. That's brilliant. Right, good evening and welcome to the second part of Sherwood Observatory Live. Right, for this part, we're going to delve right into the winter night sky that is visible for 8 p.m. today. So essentially what we're looking at is a virtual night sky stimulation of our location, and should you stand outside and face south from a dark location, this is what you should be able to see. Okay, so within the light polluted towns and cities, then obviously the brightest stars will only be visible, but in this image you can quite clearly see the Milky Way is visible running up the center of the screen. Okay, so the winter night sky is a wonderful sight to behold, and it offers the observer countless treasures to discover. I'll just move on to the next slide. Just bear with me a second. There we go. Okay, so to those who are familiar with the night sky will know that these stars form patterns in the night sky. Just zipping too far across, just bear with me, apologies. Okay, so those that are familiar with the night sky will know that the stars form patterns, and you can put imaginary lines between the stars to form what's known as constellations. And the winter sky offers some of the brightest stars to be seen. Sirius, the dog star located in Canis Major, is the brightest of them all. Sirius is so bright and not far from the horizon, it can be seen scintillating the colours of the rainbows. Okay. And you can see here well-known constellations such as Orion in the centre of the screen. Up from Orion, we've got Gemini, the twins, further up, Auriga, the charioteer, Cancer, the crab to the left, and Leo, the lion, over to the east. And what really stands out well is the Milky Way running from overhead all the way down south through Canis Major to the horizon. So what is fascinating about the constellations is that they represent an animal, a mythological person or creature or inanimate object. Here we can see an overlay of some art depictions of the constellation names, and a few really do look like their namesake. For example, Leo really does look like the lion, the head there you can see in the southeast. Okay, and we have Gemini, the twins, the two stars, Castor and Pollux, represented where the heads are, and also Orion depicted as a hunter. Okay. In mythology, Orion was boastful that he could catch and kill any animal or creature on the planet Earth. And here he is depicted with the club held high in his hand with his catch in the other hand. Okay. And just to point out, in the entire night sky, there are 42 animals, 29 objects, and 17 human or mythological characters up in the night sky. Okay, in this slide, I hope it's not too confusing for you, but it really is to illustrate how the night sky is configured. The constellations essentially have well-defined boundaries of known area. If we were to count all the segments that cover the entire night sky, then there would be 88 of them. Okay, so that was set in 1922 by the International Astronomical Union. Okay, so the blue horizontal line going across the screen from east to west is the celestial equator. It's really an extension of the Earth's equator projected onto the night sky. The yellow arc above traces out the ecliptic, which is the path the sun appears to follow while the Earth makes its year-long journey around the sun, and is consequently the plane of the solar system, hence why you can see the planet Mars raised slightly above the ecliptic in Aries, a zodiacal constellation. Okay, so here we have the prominent constellation of Orion, and it really does dominate the evening skies this time of year. And what really does do this constellation justice is to take a camera and point it at Orion and leave the shutter open for a few seconds or a few minutes, and the results can be very rewarding indeed. Okay, so this image was taken by Daniel Monk, and it truly is astounding. It is really one of my favourite images, and Daniel Monk is an astronomer at the Sherwood Observatory in Northumberland, and this was taken a few weeks ago, and it really does make Orion look pretty gorgeous, and some well-known features are beginning to stand out within Orion itself. Okay, so taking exposures a little bit deeper reveal something of the order of this picture here. Okay, so some features on this image are really worth pointing out. So we have Betelgeuse. Okay, so it's a red supergiant star. It's nearing the end of its life, and it's red because the surface temperature is about 3,000 degrees. If the surface temperature is higher, say 5,500 degrees, then it would have the similar colour to our sun. Okay, and that's big enough to fill the orbits between Mars and Jupiter. It is truly a massive red giant star. Opposite, we've got Rigel, which is a blue hot supergiant star, and it's blue and it's hot, and its surface temperature is about 12,000 degrees Celsius. Okay, other stars are Bellatrix, forming the other shoulder of Orion. We have Saph, which is the foot of Orion. Okay, and of course we've got the famous belt stars of Orion, the three in a line, the three stars that are the bottom left of the three is Alnitak, the middle one Alnilam, and the top right one, which is Mintaka. Okay, these are characteristic stars that stand out beautifully in the winter night sky. Okay, and there's a few other obvious features on this image as well, which I shall label now. And what is most noticeable about pretty much of Orion is populated by a reservoir of cold molecular hydrogen gas, known as the Orion Molecular Complex. And here on the left, we can see Barnard's looping ground, okay, and also at the top of Orion we've got Lambda Orionis. Okay, so these gaseous regions are glowing red by the ionization of hydrogen gas, and that's predominantly what all this gas in space around Orion is. It's just pretty much hydrogen gas and dust. Okay, so the exact origin of Barnard's loop is unknown, but given the shape of it, it's probably the remains of a supernova explosion. And nobody really knew this area existed until Edward Barnard discovered the area in about 1894 on some photographic plates. Okay, and it's really the Orion Nebula, which is a really small part of the Orion molecular complex below the Orion's belt, that is really the focus of our attention tonight. Okay, so this Orion Nebula image is taken by the Hubble Space Telescope. And you can see it as a misty patch below the belt of Orion. And as stated here, it is 1,300 light years from Earth. And what is good about the Orion Nebula, that it allows us to study star formation in quite close proximity. Here you can see bright big stars, there are small stars embedded within Orion, and also the Orion Nebula contains failed small brown dwarf stars as well. And through various trigger mechanisms and gravitational instabilities within the gas clouds, you know, the gas regions actually contract under the force of gravity to form new stars. Okay, so that's essentially what's going on within the Orion Nebula. As the gas contracts, it heats up, a bit akin to like a bicycle tire pump getting warm on each compression. Given sufficient mass and gas in the right conditions, the core can reach millions of degrees to a point of nuclear fusion, and a star is born. Okay. And that's all really happening within this nebulous region in the sky. And the reason why we're seeing the nebula the way we do is because of four key stars in the centre, known as the trapezium. So right in the heart of the brightest part of this Orion Nebula are 4 key stars known as the trapezium. And this is what we're going to take a look at now. As you can see, the trapezium cluster, hot energetic stars in the core of the nebula. Okay, so the trapezium is a conglomeration of thousands of stars, but essentially there are 4 main stars that stand out that form the shape of a trapezium. And what the trapezium has done, it's blown a cavity in the heart of the nebula, which is why you can see into it. The brightest star is Theta 1 C Orionis. There's approximately about 38 solar masses, so it's got 38 times the mass of our own sun. And this one star alone is actually sufficient to create the Orion Nebula. Okay, as it is the hottest and most biggest star in the area. The hot stars radiate out copious amounts of ultraviolet radiation into the surrounding gas. Ultraviolet radiation is energetic enough to actually ionize the hydrogen and make the whole region light up like a Christmas tree. Okay. And Orion Nebula is interesting as well as a star-forming region in that it's been observed by the Hubble Space Telescope to host what is known as protoplanetary disks within the Orion Nebula. And these appear to be very early stages of solar system formation around a brand new young star, and could well be disks of dust and gas that possibly coalesce into a system of orbiting bodies over time. And I believe that the Hubble Space Telescope has documented well over 100 of these within the Orion Nebula. And I believe it is hoped that once the James Webb Space Telescope becomes operational, it will peer into the heart of the Orion Nebula and peer through all the swathes of gas and dust and actually have a better look at these images and give us a better understanding of processes of formation of new stars and planetary systems. Okay, so that's some interesting new science that we're looking forward to with the James Webb Space Telescope, and that will just serve to actually do these images more justice. Okay. Right, so on to the next slide. So this slide is a flight through the Orion Nebula in different wavelengths. Okay, so what you can see here is a visualization that explores both the visible and the infrared light. And it begins with a wide field view showing the plane of the Milky Way galaxy. And if you can see this clearly on the screen, you can actually just make out Orion in the center, and you can see Barnard's Loop, as I mentioned, arcing round just offset to the right. You might notice a few other bright stars, Sirius, where you've got Orion's belt pointing to it, and over to the right, you can see a little white streak, and that is actually the Andromeda galaxy. So if I just press play on this, so what the video is doing, it's homing in on the Orion constellation, like we've just seen. And what we have is a visible light observation from the Hubble Space Telescope, okay, and also an infrared light from the Spitzer Space Telescope. The Spitzer Space Telescope is an old infrared telescope that was sent up in about 2003. It's come to the end of its life now, and it peers through the gas and dust. Okay, so hopefully this will play smoothly for you. So based on all the data from the Hubble Space Telescope and the Spitzer telescopes, NASA and scientists have created a 3-dimensional model to actually fly through the nebula complex. I mean, the Orion Nebula, it's very close, it's very big, it's well documented. It's one of the closest star-forming regions to Earth. A lot of these stars in the image are real. The distances are well known and documented. And you can see as we fly through the clouds of the Orion molecular cloud, which is a whole lot more of it below the screen, but this is just the surface of the Orion Nebula, where you can see the conglomeration of really the hot energetic stars that are newly born. They're throwing out copious amounts of ultraviolet radiation. They're actually clearing the cavity. There's a big cavern there, and you can see the universe space up above, where they expect is where planet Earth is in our solar system, and that's why we can see into the heart of the Orion Nebula. Okay. And what you probably can see from this visualization as well, a few objects coming towards you that look like mini solar systems in formation. There's one approaching now, and those are the protoplanetary disks as we spoke about. And let the video run through to the end, just to allow the credits to come up at the end to give it some justice. Okay, I hope you enjoyed that fly through of the Orion Nebula based on images by the Hubble Space Telescope and the Spitzer Space Telescope. And obviously we have to give due credit. Right, so on to the final part, which would have been live telescopic views of the Orion Nebula through a telescope. The weather is not playing ball this year. The weather has been pretty dismal around the British Isles. I did manage to capture some clear skies at the start of January, and the footage you're about to see of the Orion Nebula is taken through my own personal telescope, which is listed as a 5-inch refractor and a colour dedicated astronomy camera. Okay. So, like I say, this was taken on the 6th of January in the evening. You can see the heart of Orion Nebula there. You can see the 4 hot, luminous trapezium stars in the core of Orion Nebula. And the exposure of this is just really about 2 seconds, 2.5 seconds. And you're capturing a lot of light from the core as well. Okay, and you can begin to see some nebulosity show up from the ionisation of the trapezium into the surrounding region. Okay, and what I'll do in a minute is just ramp up the exposure time to about 15-16 seconds. That will allow for more detailed look of the Orion Nebula. And that's actually underway at the moment, hence why the image has gone a bit dimmer. But it's only gone dimmer, and it serves a purpose well in the sense it actually highlights the trapezium rather nicely at the moment. And you can see the brightest one out of the 4 dots there is actually the Theta 1c Orionis star, which is 38 solar masses, and is the one solely responsible for creating and illuminating the Orion Nebula. And there you have it. Okay, so we've got the core that looks to be overexposed at 15 seconds, which is just an indication how energetic the Orion Nebula is. The energy coming from the centre of the core is immense, and to get decent photographs of the Orion Nebula is quite challenging, in the sense that you need long exposures to tease out the intricate sort of dust lanes in the outer regions of the Orion Nebula, but also short exposures to actually get a decent image of the core of the nebula. And if I was to film this for many hours, then obviously you can stack all the data and produce a nice, wonderful image and have a nicely balanced, calibrated image of the Orion Nebula, which I'm sure you all know and love and seen before. Okay, so you probably noticed on this screen there's a bit of a dark dust lane between the Orion Nebula and another object down to the lower left, which is a circular sort of object, and that's another object in its own right, and that is known as M43. It's designated M43. That's circular nebulosity with a single central star. That single central star was just solely responsible for lighting that immediate vicinity up, and I think it's known as Deep Marian's Nebula. I think it was first identified as an independent entity to actually the Orion Nebula, which is designated M42, back in about 1731. Okay. And I think some recent papers actually have deduced that M43, the big bright star with the nebulosity, the circular patch just below Orion Nebula, is actually moving towards Orion Nebula, and it's proposed that that movement or shift into it is a reason for the stars actually coming about in the first place. If you're going to disturb a big gas cloud, you give it a shock, then what generally happens is it instigates star formation, and it's believed that through analysis of the stars and the gas movement in that smaller nebulosity region known as M43 is actually moving slowly towards the bigger Orion Nebula, and it's believed that instigated star formation probably as little as 3 million years ago. Okay, so that's essentially all I can give you in terms of a live feed of the Orion Nebula. If it was clear tonight, then obviously I think I may have taken the exposure a lot further, but at the moment we are on 15 seconds to give a balanced view of the nebula, of its core and outer regions. And I hope you've enjoyed that and look forward to any questions after. Okay, just stop sharing that.
Thank you, Brendan. Don't know if Rob and Chris have been monitoring the chat and whether there's any questions that you want to feed into us.
Yeah, this is Chris here. I've been answering questions as we've been going in YouTube. There is one I actually don't know the answer to, though. One of them is when might Orion Nebula's stars die out? So I actually don't know how hot they're burning at the moment in the nebula.
They're blue, they're hot and very energetic, in the order of probably 10,000 degrees surface temperature. Maybe I would have thought, as a guess, I don't know to be sure, but a colour of a star, such as those in the Orion Nebula, are an indication of how hot they are, really. And it will only serve to actually dissipate the nebulosity over time. I think order of millions of years, the nebulosity will disappear and the stars will become free entities in space alone and be a nice star cluster. And you probably won't see much nebulosity around it at all. And other clusters like that exist in the night sky. I think the Seven Sisters, with the Pleiades star cluster, has lost a lot of its original sort of birth nebulosity.
Yeah, just to add to that, as a general principle, bigger stars have shorter lives. So if you look at the size of our sun, it's got a lifetime of about 10 billion years, and it's about halfway through that at the moment, 4.75 billion years, something like that. If you go to stars that are many times larger than the sun, like the one Brendan mentioned, 38 times, that'll have a proportionately shorter life. And when you get up to the really big ones, you start measuring the lifetime of the stars in terms of millions of years rather than billions of years. Conversely, if you go down to the red dwarf stars, so like Proxima Centauri, for example, which is the closest star to ours, they'll last many, many more billions of years than our sun. And in fact, red dwarfs make up the majority of stars in the universe, and the reason for that, or at least in our galaxy, and the reason for that is because they live so long, none of them are burnt out yet.
Yeah, that's a good answer. Thank you. We've got a couple of others on YouTube. So here's one. How many stars? Hang on a second. How often do we think a new star might be being produced in the Orion Nebula?
Crikey. Steve, answer this if you can, if you know the answer. I'm uncertain, to be honest with you. I mean, it's a process that takes the order of millions of years, really, thousands to millions of years. I'm unsure, to be honest.
If you give me a moment while you're answering other questions, I can tell you what it is for the whole galaxy, but I have to find it first.
Okay, yeah, there is something else we can ask. So, we can see the Orion Nebula in binoculars. So what else would you recommend that can be seen in binoculars for somebody just starting out in the hobby?
Yeah, the Orion Nebula is a great starting place during the autumn and winter times because it's big and it's bright and it's obvious where to look below the Orion's belt. You're talking nebulosity objects, really. Star clusters is a good one for binoculars because they're generally more dispersed over the sky. Yeah, have a look around the Pleiades, Hyades star cluster. Try and sweep regions of the Milky Way, through Cassiopeia and Cygnus regions, really, and just really try to get a star map and learn your way. There's numerous and countless objects and jewels and fuzzy objects up there worth looking at, and it all depends what time of year as well.
Okay, good. There is another one. What sort of size are the stars in the Orion's Nebula?
Well, like I said, Theta 1c Uranus is 38 solar masses. I mean, take that as the upper example, really. Any other star would be less massive than that. So anything from a mass less than that of our sun, of one solar mass, all the way up to 38 solar masses, really, is your answer. In terms of diameter, I'm uncertain. Likely to be larger diameter than our sun, I would have thought, even though our sun is an average star, believe it or not.
Thank you. Yeah. One for Steve. When might we get our planetarium?
Are you sure that's a question from the audience and not just you?
I'd like to know as well, but yeah.
When do we get our planetarium? Well, we've been delayed a bit by COVID because the grant funding bodies were closed, so they're just all opening up again. So roughly, we think that we'll be doing the designs next year, so 2022, building it in 2023 and opening it at the beginning of 2024. So we'll be all open and running before NASA land the next humans on the moon, hopefully. So that'll be a great event to watch from the planetarium dome, I suspect.
Okay, cool.
If
There's
anyone
one.
wants, I can do a whole presentation on that now.
Watch this space. Yeah.
Yes.
There is one in Zoom from Andrew. Why has the James Webb Telescope got no optical component?
Why has it got no
Optical component?
You mean visible as in?
I believe it means, yeah. Why can't it? Yeah, see invisible light. Yeah.
Yeah, it's it was a design choice. One of the main reasons for the telescope is to look back into the distant universe and look at the first stars and the first galaxies and things like that. Now, because of the universe is expanding, the further away you look, the faster things are receding from us in terms of expansion of the universe, and that stretches the light. So what was visible light, because it gets stretched into longer wavelengths, becomes infrared light. So the light that it's looking at would have been visible when it set out, but it's turned into infrared light when it gets to us. So you have to take that into account when you design the telescope.
Yeah, so it's interesting to note as well, Steve, that the James Webb Space Telescope mirrors are actually made of beryllium, which is lighter than aluminium, and it's more forgiving on thermal expansions and shock and whatnot, and the gold covering is highly reflective in the infrared as well.
Yeah, one of the things I meant to mention and forgot is that this telescope's going to be working at minus 260 degrees C to sort of round about that, very, very cold. So they've actually had, and obviously that's not the temperature on Earth. So when they build all of the optical components on Earth, they have to make them the wrong size, because everyone knows that when you warm things up and cool things down, they expand and contract. So the entire thing is built to be the wrong size, so it becomes the right size once it gets to its working temperature. So if you test the optical components in a lab on Earth, it won't work. So they have to, and one of the, as Brendan says, one of the things about beryllium is it doesn't expand and contract very much at different temperatures, so it's easier to do that than some materials.
Not sure if the question on the sails, the foil sails on the Webb telescope has been answered. What stops the sails from becoming a clump of tin foil, like a Kit Kat wrapper?
Yeah, so Nigel's asked a question on the chat saying, where's the James Webb going to be positioned due to the delicate nature of the reflector shield? Are we assuming that's a safe area from other space debris peppering the shield? Yeah, that's a good question, Nigel. It will end up with holes in it due to micrometeorites. And when I said it was going to be parked at the Lagrange point, that is naturally a place where junk accumulates. Although these pictures you get of asteroid fields in science fiction films where the spacecraft's having to weave around the asteroids isn't right. They're still like millions of miles apart, so there's a lot of gaps. But what they've done with the shield, because it isn't strong enough to withstand anything hitting it, particularly the speed things move in space, is that if anyone's used like rucksacks or outdoor gear, it's made out of a lot of it's made out of material called ripstop nylon. So if it gets a cut in it, it doesn't spread. They've kind of adopted the same philosophy with the shield, so it's got sort of woven into it or stuck into it, I guess. It's made of lots of different cells with reinforcement. So if one bit of it gets a hole in it, that hole won't tear all the way across the whole thing and make it fall apart. It'll just stay as a small hole. And it's not like it's got to keep gas in or anything. So if it gets a few holes knocked in it, it'll not affect it too much. I mean, obviously, if it gets hit by a big meteorite, it'll smash the thing to bits and it'll be gone. But I guess that's a chance you've got to take on any space mission.
We've got a question from Rick Hall asking if what involvement the UK Space Agency and ESA have had on the design of the Webb telescope.
Not so much the actual physical big structure of the telescope itself, but we're very good at instrument manufacture in this country. So the team have been working on the optical components and the instrument itself. I mean, the British team have led it, but it's actually been an ESA consortium. So there's been people from various European nations who are members of ESA working on that as well. Just to have a quick kind of Brexit note on this, the European Space Agency is an entirely separate organisation to the European Union. So our membership of the ESA, I don't believe, is affected by us leaving the European Union.
Are visitors allowed to visit the reservoir?
Visitors aren't allowed to visit anywhere at the moment, unfortunately. Yes, we can take limited numbers of people down the reservoir once we're open for business again, and we have done in the past. We're trying to make it a little bit safer and a little bit cleaner when we reopen, but yes, we hope to do that. And yeah, Barry, just in response to your question, there isn't really any protection for it, other than, as I say, making sure that the shield doesn't rip all the way across from one side to the other if it gets a hole in it. But space is a very, very big place, and there's not much stuff in it on average. So hopefully not too much chance of it getting whacked by something big enough to damage it.
What's the anticipated life span of the James Webb, Steve?
Oh gosh, you know, I can't remember that. It's a bit like a lot of space telescopes. The lifespan isn't dictated by the thing breaking down. It's dictated by how much propellant it's got on board to keep it pointing in exactly the right place. So it has like maneuvering thrusters that keep it on station. One of the things about Webb, and I think it's because it's so big, because of the heat shield, it's actually going to get pushed by radiation. So it's big enough to act as a small light sail and potentially get propelled. So one of the things that the attitude jets have got to do is keep adjusting to counteract pressure from photons hitting it. I mean, it's not very much, but it doesn't need to be very much given the accuracy that the thing's got to point at when you're that big a telescope.
Wow. Any more questions? Don't be shy.
No, that's it at the moment.
There was one about where's James Webb being built, and I believe it's California. It might have been built at JPL and then moved to Northrop Grumman for testing or something.
Yeah, I think so. Yeah, as I say, you know, various bits of instrument have been built all over the world, and I think going back to the beryllium, I was reading earlier on that the beryllium was mined in Ohio. I think you knew. So yeah, and it's going to be launched from French Guiana, so they've got to get it there without breaking anything. But one of the things they do when they're testing, because obviously when you launch something, if you ever see video of astronauts sitting in any launch vehicle, whether it's a space shuttle or the conventional rocket, they get rattled all over the place. So one of the things that they always do to test a space telescope or anything else to launch into space is to do a shake test on the ground to make sure nothing falls off it. And when they did the first shake test on Webb, things did fall off it. So they had to kind of securely bolt things back on again. It was actually supposed to be launched a couple of years ago, but they had some difficulties with it, including, as I was just saying before, it has attitude jets to make sure it keeps pointing in the right direction. And someone washed the attitude jet nozzles out with the wrong solvent, and that ruined them. So they had to start again and build some more, just because of one simple mistake, someone rinsing something. When you look at all those pictures I showed, the reason why they've all got masks and hats on isn't because of COVID. It's to keep dust off it, because you've got all those moving parts and very sensitive optics. You get a couple of grains of dust in that, then you've got no way of cleaning it once it's up there. So that's it. The image is spoiled. So that's why they take such careful precautions.
A question has popped up, Steve. How many light years can it see? How far?
Well, they think it should be able to see back to first light in the universe, which from memory is a few 100 million years, 500 million years or something like that. They think first light, maybe something like that.
Yeah.
So that would be 13 billion light years thereabouts. It depends because it's looking back further than anybody else has looked before. Boldly going where no one else has looked before, I suppose. They don't know what they're going to find. So there's been all sorts of researchers coming up with theories about what they might find, and some of those theories include the first ever stars, which were massive stars, like hundreds of times bigger than the sun, and therefore burnt out very quickly. What it would be able to see is depend on how big they are, therefore how bright they are, and they don't honestly know. I mean, even Hubble, they found stuff that they didn't predict. So they're kind of predicting, if you see what I mean. They're going to find things that they didn't predict.
Yeah, I think you're right. Telescopes in general are limited by the universe itself rather than the actual telescope.
Yeah.
So in terms of that barrier of the first light is its limits, really.
Yeah. So they've got, I think it was Donald Rumsfeld who said, there's known unknowns and unknown unknowns. And they know a few unknowns they want to test, but there's also they're expecting to find unknown unknowns that'll change how we view the universe.
I just wanted to point out, it wasn't just Galileo we got chucked out of because of Brexit. There was there's at least 3 other ESA projects we've been thrown out of for no obvious reason. And it's reported that the new boss of ESA is worried about EU encroachment. Now, I know no more than that.
I don't know. I don't know about that. I'll pass on answering that.
But these projects, they look quite innocuous to me. Just things like environmental survey work. We appear to be put out on our ear. I mean, I know
we just had an answer to the question I didn't know the answer to, which is from Sparky, who says the lifetime of James Webb's supposed to be 5 years with the possibility of another 5 years. These things do tend to exceed their design life, so thanks for that. Right, there's another question. What are the plans for what will be done if it doesn't work properly when it gets there? I think there'll be a lot of upset people sort of crying, really. So there isn't a plan. If it doesn't work, it doesn't work.
Okay, I've had another couple of questions come in. There's one quite easy one to answer, another one a bit more difficult possibly. So what happens to the telescope when it reaches at the end of its life, when it's out there orbiting L2?
It'll just become another piece of space junk.
Yeah, I mean, there's already a few dead ones there, isn't there?
Yeah, because it's been known as a good place to park stuff for a while. So
yeah, and then here's another one. So seen, where is it? I forgot where I've seen that in history. Okay, it's something like seen as it's peering so far back into the universe, why doesn't it use radio waves rather than infrared? That's probably a redshift question, I think.
Yeah, I guess it probably is. I guess it depends what you want to look at. I mean, we do have radio telescopes that look a long way back, and I guess the furthest look back is in microwave wavelengths, because we look back and we see the cosmic microwave background radiation, which is the earliest thing it's possible to look at. So I guess you pick your wavelength, you take your choice. I
guess the thing with radio as well, you'd need a correspondingly much larger dish, which we currently don't have the ability to get up there.
Yeah, I mean, there's been talk, obviously, about the distant future of sticking radio telescopes on the far side of the moon, so you're shielded from radio interference from Earth. But obviously, that's a good way into the future. But yeah, that's a good point, Chris. The size of the mirror has to go up with the length of the wavelength, so you need bigger and bigger mirrors the longer and longer the wavelength you get. So. Yep. That's why radio telescopes are huge.
Okay, loads of questions still coming in. So is the JWST going to be deployed at a similar distance to where Gaia currently is?
I don't know off the top of my head where Gaia is, actually.
No, I can answer that one, actually. No, Gaia is at L2, so
right.
I didn't realise that until I've just checked now. So yes, it's the same place. It's a good spot for space telescopes.
Hopefully they won't crash into each other. That would be embarrassing.
Yeah. When will Hubble be retired?
When we
Now,
start
which
getting
isn't it?
useful
It's
information
about
from
on
it.
its last legs now, isn't it?
It's way beyond its
Yeah.
expected end. I guess they'll just keep it going for as long as it keeps working, I guess.
Actually, Angus has just pointed out the atmosphere is transparent to radio, so you don't really need to launch radio telescopes. It's more about interference from man-made stuff that broadcasts radio waves on Earth than needing to look through the atmosphere for radio astronomy. That's a good point.
Okay, cool. And then, yeah, how can the telescope detect the atmosphere of a planet?
Right. Got another whole talk on this one. In fact, I'm writing a dissertation on this one. So there's a number of different ways, but there's two ways that Webb works is going to do that. One's the most important way. So if you imagine a planet going around another star, if the planet is going around the star in the right orbit, every so often the planet will come between us and the star. So if you imagine the planet transiting in front of the star, the same way that we can see transits of Mercury and Venus from Earth, some of that starlight will shine through the atmosphere of the planet on its way to us. And the molecules that atmosphere is made up of will absorb some of that light in a characteristic way. So if Webb can measure the spectrum of that light that's gone through the upper atmosphere of the planet, it can work out what the composition of the atmosphere is. The other way that it can do it is measure the planet's infrared signature. So, a planet's warm and it gives off light like or heat like our own planet does. And again, if you analyze that signature, you might be able to say something about what the composition of the planet is. People have done that to test it with our planet by measuring the Earth glow off the moon. So when you've got a new moon, you've got sunlight reflecting off the Earth, hitting the moon and reflecting back to the Earth again. And if you analyze that light reflected back off the moon, you can pretend you're looking at another planet. And one of the things that they've found is if you look at the reflection of the Earth off the moon when the Amazon rainforest is facing the moon, and then you do it again when it's just the Pacific Ocean facing the moon, you can see a difference, and that difference is put down to green plants in the Amazon. So if you saw something like that, you might be able to infer that there's vegetation on one of these other planets. Very hard to do, though, very hard. And I think whatever you found, it wouldn't just be a big bang, we found aliens. There'd be arguments left, right, and centre about whether that's what it really meant or not. The killer finding would be if you detected something like a chlorofluorocarbon in the atmosphere, because they have no natural source and they're in our atmosphere due to man-made pollution. So if you found a chlorofluorocarbon in the atmosphere of an exoplanet, you'd be able to say with a reasonable degree of confidence that there was an industrial civilization living on that planet. There's a thought. You have more?
I don't think I've got any outstanding questions.
So viewers in Zoom can unmute themselves if you want to speak.
Okay, there was one about does the telescope monitor asteroids that could be heading towards Earth? I think I could probably answer this one. It's not really in the remit of James Webb to do this. That's more a job for the survey telescopes that exist on Earth that scan the whole sky every couple of days.
Webb will be looking at stuff within our solar system in high resolution, as well as
Yeah.
looking at stuff further
But
away.
it's not specifically for near
scans.
Earth objects or anything like that. No.
Yeah. Well, since we've still got a few people on and the questions are drying up, what I could do is run a video, an animation of what we want our new Science Discovery Centre and Planetarium to look like, just out of interest for people on. So why don't I share my screen and do that? If I can find what I've done with it, which I can't. Give me a moment.
Can you do it?
I've got to just find the right. It's not playing ball for some reason. Bear with me.
May I ask a question whilst we're waiting?
Yeah, of course.
I'm sort of really keen to become a member, and I keep looking at the website, and I'm just sort of waiting. I take it all has to wait until COVID stops, or is that right?
No, it doesn't. You can join whenever you want. Obviously, you get more benefits when COVID stops because you can actually physically be at the observatory. But we are trying to do online stuff for our members as well as events like this. So we have we have a Wednesday night members meeting. We have a monthly guest lecture, sometimes by a professional astronomer, sometimes by an amateur astronomer, sometimes by one of our members. So yeah, you can join anytime you want, right. Or you can wait. Yeah,
I'll have another look because I didn't get that impression. But okay, thank you.
Okay, well, hopefully our website doesn't give that impression. It shouldn't.
It was a while ago. But I will check again. Thank you.
Yeah.
Thanks.
Okay. Right. I'll see if I can run that now. Thanks for filling in for me by asking that question. Right. So this is just about a minute and a half. So I'll just run this, give you an idea of what our plans for the future are. I never tire of looking at that.
Wow.
Taste of the future, eh?
Absolutely. So if anyone wins the lottery, think of us because we need money. Although we have got a couple of major funders, hopefully thinking about it at the moment. So, but the link I put on right at the beginning of my talk is on our website as well, and we are collecting money for the 10% contribution we have to make to the design money we'll be getting from elsewhere. So if you've liked what you've seen tonight, as Bob Geldof would say, give us your money.
It's the only way.
We've had some great support from businesses in the area, both in terms of work in kind for us, and in terms of direct donations, actually. So we're well on our way.
Yeah, all I can say is watch this space for future events from Sherwood Observatory live over the next few weeks and months. I hope with the weather improving and longer days, we'll have some solar observations during the daytime as well.
And a quick plug for the Orion star count, Brendan. When does that end?
I believe it's tomorrow, the 14th, I think, is the last day for the Orion star count. I know I didn't mention it, but if you can count how many stars are in the constellation of Orion, omitting the 4 corner stars, but include the belt stars, then that needs to be submitted to the, is it the Campaign for Rural England, I believe?
Campaign for Protection of Rural England, yeah.
Yeah, correct. I'll collate in the data for that. Yeah, so that's worth doing. If it's clear, of course, of which it's probably not.
Yeah, we've not had a good year for clear skies.
No.
We've
Right,
had
sorry,
late question come in. If we spend a couple of £100, I presume that means on a new telescope, what can we expect to see other than the moon?
That sounds like a question for you, Chris.
Do you want to answer it? Or?
Yeah, go for it, Brendan.
No, I thought you want to answer it.
You can see a lot. You can see a lot more if you train yourself to see it as well. It's a difficult question to answer quickly. I wouldn't spend any less than a couple of £100. But there's a lot of stuff out there you can see for that.
Or you could, a couple of £100 would buy you 4 years worth of membership of MSAT, and you could be trained to use our very large telescope, and we also have smaller, high quality telescopes that you could use as well. So there's an alternative. Not at the moment, of course, because we're closed, but when we open again.
Yeah, essentially point the telescope at any bright object that's not the sun and just interrogate it as best you can and learn from it.
Yeah, or binoculars. I think we always recommend binoculars can be a good place to start.
You can see lots of things just with the naked eye without any optical aids. Deep sky objects.
Clouds.
Yeah.
Okay, there's 2 more questions, so they're still coming in. How much do we need to raise towards the planetarium, I presume?
Right. It's cheaper than the James Webb Telescope.
By all means, yeah.
Right, I couldn't have answered this question yesterday because we hadn't told our funders, but our funders now know, so I can. And the answer is in 2 parts. We need to raise £22,500 as matched funding for the next stage, of which we're a bit over 20,000 already, so we've only got a couple of thousand to go there. The whole project in its entirety from start to finish is somewhere around the £6 million mark. But we are talking to 2 major funders for a sizable chunk of that at the moment. Not guaranteed, it's going to be tough, but you know, things worthwhile are never that easy.
So what's the time scale, Steve, when we put the beds in and things like that? The timeline on it?
Sorry, say that again?
So what's the timeline we can expect on the Planetarium Science Discovery Centre we have now, the new one?
Okay, so this year it's sorting out some of the funding pots because the funders have been closed for a year due to the pandemic. That, if all that goes well, we'll be appointing the design team at the end of the year, you know, for the detailed design and all the planning permission, all the engineering studies and things like that. That would take most of next year, so 2022. We then appoint the main contractor at the end of next year. They'd spend all of 2023 building it, and then we'd be opening in 2024. Is very blocky, very lumpy timetable, but that's roughly how it works out.
So
don't hold me to it, because I thought we were going to be a year ahead of that, and then look what happened in the last year.
Okay, and we've still got questions coming in. This one's a bit more generic. Which of the current space projects are you most excited to see the results of, like going to Mars, the Moon, Elon's projects, or Richard Branson's Virgin Galactic? I think this is a personal thing, isn't it, for everybody?
Well, we've got Perseverance landing next Thursday, the 18th. It's being streamed live by NASA, so that'll be really exciting. So that's something.
I think current missions are always exciting, but I think the big prize and the big goal is the James Webb Space Telescope. Really, I think the capability of what that's going to deliver long term will outstrip everything else. I think.
A little bit like
if you imagine life before and after Hubble, then that Hubble changed everything in this world as well. And other than that, if you look a little bit further in the future, you know, I got interested in astronomy like a lot of people by watching the moon landings, and you know, we might be there again in 3.5, 4 years time. So yeah, that's one to watch.
It's just the golden age of exploration, what's happening, isn't it? It's just space missions are overlapping each other. It's difficult almost to keep up.
Indeed.
Is it Juno's coming to an end this year, September time, I think? It runs out of fuel. Orbiting Jupiter.
Right, it feels like we're coming to a natural end almost, I think.
Okay, shall I just wrap up then, Brendan?
Yeah, absolutely. By all means, we need to.
Okay, well, for those of you who still are left that we haven't scared away yet, thank you for joining. Hope you've enjoyed it. Visit our website or look on our YouTube channel. We've got quite a collection of recordings from both professional astronomers and amateur astronomers on our YouTube channel. So have a look at that. Keep an eye out for when lockdown is lifted and we can reopen the observatory again. And we hope to see you there in the fullness of time. So thank you for joining us, and thank you to my colleagues for tonight as well. Remember, we're all amateurs and we just do this because we enjoy it.
Thanks very much. It's been really interesting.
Okay, cheers, Paula.
Thank you.
Okay, great.
Okay, good night, everybody.
Night.
Good night.
Night night.
All right.
Good night, Sheena. Angus.
Do we stop recording?
I'll disable the live stream now to YouTube. Goodbye, YouTube.